All right, so welcome to Chapter 7. Chapter 7 is all about applications of integrals. And this chapter, you're going to see a bunch of cool stuff. You're going to see how to find area in a plane. You're going to be able to find the volume of certain solids. You're going to be able to find arc length. But all of those come back to one basic concept of integrals. Integrals allow us to accumulate a rate of change. And that's all what what section 7.1 is about. Integral as a net change. So here in this example, I have a honeybee making several trips from the hive to a flower garden. This right here is the velocity graph. So you can see the bee starts out, he's traveling 100 feet per minute for 2 minutes. Then he takes a little bit of a break for 3 minutes. Then he travels at negative 100 feet per minute for another 2 minutes. Then he takes a break for another minute. Then he travels positive 100 feet per minute for another 2 minutes. And then takes another break for a minute, and then travels at negative 100 feet per minute for another minute. So in order to find the distance, what we need to acknowledge with distance, it doesn't matter whether you're going forward or backward. Like, it doesn't matter the fact that this is 200 feet in the forward direction because we have these this positive velocity. It does not matter that this is going 200 feet in the reverse direction because we have a negative velocity. Basically, what we're trying to say here, when we calculate our total distance, we need to take away any negativity from our velocity function. And the way that we write that we have taking away the negativity, we use a certain operation where we say the distance is equal to the integral from the beginning of the journey to the end of the journey of the absolute value of the velocity. So the key concept here, we're talking about taking each of these distances that they traveled and not caring about whether the bee was going forward or backward. So the distance that this bee traveled is going to be the absolute value of the 200 feet when it moved forward, plus the absolute value of this negative 200 feet when it moved backward, plus the absolute value of this 200 feet when it moved forward again, and then plus the absolute value of this negative 100 feet when it moved backward again. And just looking at that, 200, 400, 600, 700. So the distance that this bee traveled is going to be 700 feet. And one thing that this really drives home, or something that drives this home in my mind is talking about running on a track. So if you've ever run a track and field event, you'll know that the distance around the track is going to be 400 meters. So if you run one lap around the track, you have traveled a distance of 400 meters. But if you travel one lap around the track, you're at exactly the same location that you started at. So we have to have a difference between the distance and another concept that comes up in this section. And that concept, instead of distance, is displacement. So here we talk about the displacement of the bee. This is kind of like a position relative to his initial position. So what we look at here, the displacement of the bee is going to be equal to the 200 feet that he went forward, but then we need to take into account that he did actually move 200 feet in the reverse direction. And we can see that negative 200 feet by looking at the area here. It is below that x-axis here. So 200 plus negative 200 plus the positive 200 plus, again, that negative 100 feet. So when we look at this concept is the concept of the signed area. So when we look at our displacement is going to be that integral from the beginning of the journey to the end of the journey of our velocity. Oops. Equal to, forgot that I had an equal sign there. And just looking at this, 200 cancels off the 200, so he's at the original starting place, then up forward 200 feet, and then backward 100 feet. It looks like this bee ended up 100 feet in the positive direction from where he started. Now we can't figure out exactly where this b is without knowing where the b started, but again we can say that he's 100 feet either forward, to the right, or up from his initial position, depending on how we're scaling out our axis. Yeah. So right about here, we have that written out in words. To find the displacement, meaning the position shift from the velocity function, we just integrate the function. And that was that second example here. The negative areas below the x-axis subtract from the total displacement. So the displacement, again, another way to think about it is the relative position considering its initial position. In order to find out the actual position of whatever item you're analyzing, you need to add on the initial position to that. To find the total distance traveled, we have to use the absolute value. So the distance traveled is going to be equal to the integral from a to b of the absolute value of v of t dt. Find the roots of a velocity equation and integrate in pieces, just like when we found the area between a curve and the x-axis. Or you can just take the absolute value of each, and then you take the absolute value of each integral. Or if you have a calculator at your disposal, you can just do the integral from a to b of the absolute value of the velocity function. All right? So looking a little bit further, we can see the difference between displacement and distance traveled using this velocity graph and this position graph. So again, if I want to talk about the displacement, I have starting off at a position of 0, between 0 and 1, I can see an area of the square is 1. So at 1, notice that I've accumulated my displacement as 1 unit. Then, in between 1 and 2, I have an accumulation of another half unit. So looking down here, that would mean at 2, I've accumulated another half unit of displacement, which would put me at 1.5. Then, between 2 and 3, I have an area of 1/2, but since that velocity is a negative velocity, I'm going to accumulate negative displacement. So between 2 and 3, I'm going to accumulate a negative displacement of 1/2, which should put me, I'm trying to look at this at an angle, should put me at the exact same position as I was at 1. Now going between 3 and 4, it looks like I'd have a square right there, which would be 1. So we can actually see right there between 3 and 4 accumulating that -1 distance, which puts me at my original position right here. And then between 4 and 5, I have that other 1, which really brings me down, lands me at the end of my journey at -1 relative distance. So here we can see that using math, 1 plus 1/2 minus 1/2 minus 2 is equal to 1. And the way that we would write that using calculus, we would say the integral from 0 to 5 of the velocity dt is equal to that. Versus the distance traveled. The distance traveled, I don't care that this is +1 and this is -1. They mean the same distance, whether I'm going forward or backward. So when I've traveled forward 1.5 units and then traveled backward 1.5 units, this distance traveled from 1 to 4 is actually 3 units. Then I add on that extra 1 unit there to get my total distance traveled of 1 plus 1/2 plus 1/2 plus 2 is equal to 4. And 2 ways that we can write that. We can write that as either the integral from 0 to 5 of the magnitude of velocity, dt, or we can talk about that as the absolute value of the integral from 0 to 1 of velocity, plus the absolute value of the integral from 1 to 2. Actually, you know what? We don't even have to go that far. We can just, as the last page said, find the roots of our velocity function, and we can just say this is equal to the absolute value of the integral from 0 to 2 of v of t dt plus the absolute value of the integral from 2 to 5 of v of t dt. Every single AP exam that I have ever seen has had at least one free response problem that involves analyzing the difference between distance and displacement. Sometimes it's in a tabular data problem, sometimes it's in a function problem, but I have seen this on every single AP test that I've ever looked at, and I've looked at a lot of them. So, is it important? I would say yes. Well, let's look. Do we have okay. So here is just a nice way of summarizing it. The linear motion equation, ds dt is equal to v of t. V of t is a function of time, so ds equals v of t dt. Delta s is equal to v of t delta t. S is equal to the sum. We get summation. We change to infinity, makes it to an integral. So what you need to know now is your position can be determined from your integral of your velocity. So let's get after it. All right. So v of t is equal to 10 minus 2t is the velocity in meters per second of a particle moving along the x-axis between 0 and 9 seconds. Use analytic methods to A, determine when the particle is moving to the right, to the left, and stopped. B, find the particle's displacement for the given time interval. If s of 0 is equal to 3, what is the particle's final position? And D, find the total distance traveled by the particle. So part A is really not conceptually it's kind of calculus-y, but it's not really ultimately that deep of a calculus question, because to determine where the particle is moving to the right, to the left, and stopped, you start by finding the third one. You find out where the particle is stopped. And a particle is going to be stopped when it's not moving. And when it's not moving is when v of t is equal to 0. So this particle, v of t equals 10 minus 2t, I set that equal to 0, and I'm going to find out the times when this particle is standing still. So looking here, add 2t, I get 10 is equal to 2t. That means 5 is equal to t using the symmetric property. Just put that as t is equal to 5. So at 5 seconds, this particle is going to be standing still. And it's possible for you to have more than one time where this is standing still. Now, in order to find out where the particle is moving to the right or to the left, there is something that you do need to have intuitive, and if you don't, or you need to have this intuitive feel for it. So if you don't have this next part intuitively in your brain, you might want to make it there. And that's just what the positives and negatives of velocity means. A positive velocity means you are moving to the right. A negative velocity means you are moving to the left. A positive velocity could also mean moving up. A negative velocity could also be moving down, depending on what orientation you're dealing with. Also, positive velocity is forward, negative velocity is backward, unless we change the system. And we'll always tell you if we're changing the system. So here, we're talking about left versus right. So left is going to be negative, right is going to be positive, right? So in order to figure out where this particle is moving left and right, I go back to this whole number line situation. I'm going to analyze v of t. I'm going to put down the beginning of the interval, where it turns around, and the end of the interval. Now, all we're doing here is we're doing a sign chart like we did so many chapters ago. Between 0 and 5, you could use a test point if you want to here. 1, 10 minus 2 times 1 would give me a, I believe that is a positive. Between 5 and 9, test point of 6. 10 minus 2 times 6, that gives me a negative, right? So now I can clearly see this particle is moving to the right, starting at 0, because that is the start of the evaluation of this movement. So from 0 up until 5, actually I would call it inclusive at 0, exclusive at 5, because technically it starts off moving to the right. At 5, it is moving neither right nor left. The particle is moving to the left between 5 until the experiment ends, until 9. And it's still moving left at 9, so I'm going to be inclusive there. And where is the particle stopped? At t is equal to 5 seconds. All right, so again here, very low, not too difficult kind of situation here. Find the zeros of the velocity function, set up your sign chart. Positive means moving right, negative means moving left. Now let's find the particle's displacement. I'm going to need a little bit of fresh paper here. I said I'm going to need fresh paper here. Thank you. Apparently I advanced 2 pages. So for part B, I want to find the displacement. So the displacement, again, we set this up a couple of slides ago. The displacement is going to be equal to the integral over the entire interval. So just the integral from 0 to 9 of the velocity function. So in order to evaluate this, again, we're using analytic methods. So we don't really want to touch our calculator here. We would have integral from 0 to 9, velocity function being 10 minus 2t dt. We know using the fundamental theorem of calculus part 1, we need to antiderive 10, we get 10t, minus antiderive 2t, we get t squared, and we're going from 0 to 9. Now, fundamental theorem of calculus part 1 tells us, evaluate at the upper. Somehow my pen completely went away. There we go. 10 times 9 minus 9 squared minus evaluate at the lower. 10 times 0 minus 0 squared. 10 times 9, 90, 9 squared, 81, 90 minus 81. It looks like this particle has been displaced by, again, 90 minus 81, 9, and we see the units as meters. So the displacement of this particle is 9 meters. So it is 9 meters in the positive direction from its initial position. So we know that it is 9 meters to the, again, the direction it's talking about is right versus left. So it is 9 meters to the right of the particle's initial position. That allows us to answer part C. Part C is asking what is the particle's final position. We know from chapter so long ago, I think it was chapter 3, we used S for position. This question is asking what is the particle's position at the end of the experiment at 9. At 9, what is this particle's position? So again, the way that we write this down mathematically, we would write it down as S of 0 plus the displacement, so integral from 0 to 9 of V of t dt. Error checking thing here, you want this position, whether it's 0 or 1 or 2, to match this position right here. The time, the 0 should match the lower limit here. So here we know that our initial position was 3. So we have 3 plus our displacement, 9. This particle on whatever scaling we have is at the 12 meter mark, however the scaling works here. Okay? So again, when you find your displacement, add on the initial position, and magically you have found the final position. Whew. Now we need to find the total distance. To find the total distance, we need to find the integral from the beginning to the end of the absolute value of the velocity. So, part D, the distance traveled is going to be the integral from the beginning of the interval to the end of the interval. 0 to 9 of the absolute value of V of t dt. Make sure the absolute value is only around the velocity. You saw I almost screwed that up, but then I caught myself. Now here, this is going to be a little bit more difficult because we need to make sure that we subdivide this into the different intervals when the particle is moving to the left and to the right. Now if we had a calculator in front of us, we probably could just type in integral from 0 to 9 of the absolute value of 10t, no, the integral of the absolute value of 10 minus 2t dt, but we want to use analytic methods, so we want to avoid using our calculator. But fortunately, we have done number A already. Number A tells us that the particle is moving to the right between 0 and 5, and to the left between 5 and 9. So if we wanted to do this without a calculator, writing integral from 0 to 9 of the absolute value of 10 minus 2t is the same thing as the absolute value of the integral from 0 to 5. Now just to remind you guys, 0 to 5 of 10 minus 2t dt plus the absolute value of the integral, our other interval, from 5 to 9 of 10 minus 2t. So this is how you have to work it if you are doing the distance traveled by hand. So now here we do recognize that we have to use two different fundamental theorems of calculus. Fortunately, since we've already done this work, we know the antiderivative of 10 minus 2t. Again, it's on the previous page, 10t minus t squared. Rocking that from 0 to 5. And then add to that the absolute value, same thing, 10t minus t squared. Rocking that from 5 to 9. Taking the absolute value there. So this is going to be a little bit messy to write it all out, but absolute value of 10 times 5 minus 5 squared minus 10 times 0 minus 0 squared. There's the first quantity plus absolute value of 10 times 9 minus 9 squared minus 10 times 5 minus 5 squared. And now just do the arithmetic. 50 minus 25, so absolute value of 25 minus 0 plus absolute value, I think we just did that, 90 minus 81, 9 minus 25. So that's going to be 25 plus distance between 9 and 25. I believe that is 16. 25 plus 16. This particle has traveled a total of 41 meters. So although the particle has traveled 41 meters, it has only moved 9 meters from its initial position, just going back to part B there. Again, really trying to drive home the difference between distance and displacement. And let me pull up my calculator here real quick. So again, just pointing out that if you had wanted to do this and you didn't want to do this by hand and you had a calculator at your disposal, you could, of course, do the integral from 0 to 9 of the absolute value of 10 minus 2t dt. You should get the same exact thing. Noticing here, we do get 40.99999999974. That's essentially just saying it's 41. All right. You could also, in this chapter, have done that for the displacement. So looking at that, I could have, if I had my calculator available to me to find the displacement, I could just do integral from 0 to 9 of 10 minus 2t dt, and I could find out that my displacement was 9 meters there. But again, you really want to shy away from using your calculator all the time, although it is possible to use it some of the time. All right, so let's look a little bit further here. I think there's one other type of problem that we really have here, and that's using the integral as an accumulation of a rate. So here, this general strategy exists on page 382. It is a pain in the butt to use, but you start by approximating what you want to find as a Riemann sum of values of a continuous function multiplied by interval lengths. If f of x is the function and a to b the interval, and you partition the interval into subintervals of length delta x, the approximating sums will have the format summation f of c sub k delta x with c sub k a point in the kth subinterval. To write a definite integral, here it'll be integral from a to b of f of x dx to express the limit of these sums as the norms of the partitions go to 0, and evaluate the integral numerically or with an antiderivative. All of that just comes into doing a problem like this. We have a rate of consumption of potatoes. So we see from 1970 to 1980, the rate of potato consumption in a particular country was C of t is equal to 2.2 plus 1.1 to the teeth millions of bushels per year, with t being years since the beginning of 1970. How many bushels were consumed from the beginning of 1972 to the end of 1975? What the previous slide was saying was, in order to find this summation, you want to find out the rate over a short period of time. That summation is going to be the sum of 2.2 plus 1.1 to the c sub k delta t. Now looking at that, we know that we want to have infinite subdivisions. So we just see a rate of millions bushels per year. We're going to rewrite it as an integral to accumulate that rate. So if you see a rate and you want to find the accumulation of that rate, you are going to write it as the integral of 2.2 plus 1.1 to the teeth dt. Do you have to do this step right here? No. It's really just to drive home the point that we are talking about the area. It's drawing it back to rams. Really, we want integral is accumulation of the rate. Now we need to find out what our lower limit and our upper limit are. In order to figure that out, we look at the beginning of time and the end of time. The beginning of time is the beginning of 1972. Now when we look at the scaling here, t is the years since the beginning of 1970. So 1971 is going to be year 1. 1972 is going to be year 2. So we're going to be doing the integral from 2 till, now here's where it gets a little bit weird. The end of 1975 is not going to be year 5. The end of 1975 is the beginning of 1976. So we actually have to do the integral from 2 to 6 of 2.2 plus 1.1 to the teeth. Now here is where we run into what strategy should we use for this problem. If I wanted to do this by hand, I would have to integrate 2.2 by hand. I would have to integrate 1.1 to the teeth by hand. If I wanted to use the fundamental theorem of calculus, this is going to be 2.2 plus 1.1 to the teeth divided by ln of 1.1 from 2 to 6. If I want to evaluate that period, I'm going to have to start using my calculator at some point. Since I'm using my calculator at some point, this problem is not to be done by hand. When we see a really weird function being integrated like this, that means we want to jump right to our calculator and just do it completely on our calculator. So I pull up my calculator. I just type in the integral from 2 to 6 of 2.2 plus 1.1 to the teeth power, whoopsies, dt, hit enter, and I can see that I have 14.692. 14.692. Again, just copying that directly off of my calculator. Now here we do have to worry about our units. So looking at our units, we had millions of bushels per year, but we multiplied by that year, so the per years cancels off, and we have millions of bushels of potatoes So it's 14.692 millions of bushels of potatoes were consumed from the beginning of 1972 to the end of 1975. And I believe that leads us into, this is the problem number 1 from the 2019 free response. Problem number 1 is usually what we call, or what I call, a rain and drain problem, where you have an enter and a leave function, whether it's water being poured into a tank and being drained out of the tank, or in this case, fish going into a lake for the E and leaving the lake for the L. And you're usually going to have to figure out, like, how many fish went into the lake, how many fish came out of the lake, how many fish are in the lake at this particular time. Very similar to this structure. Hopefully tomorrow we'll be able to go through that, that problem, at least in part. But here's your assignment, and I will see you guys after the break. I keep saying tomorrow, but I keep forgetting that some of you might be watching this over the Thanksgiving break. So I hope Thanksgiving is going well for you. Goodbye.